Hey, physics students, Mr. Heinrich here, and we're here with another projectile motion problem. We got a quarterback who throws the football to a receiver who is 31.5 meters downfield. They're throwing at an angle of 40 degrees. And once again, this is a difficult problem, or I should say more difficult than some, because they don't give us VI. So we're going to need a system of equations. We're going to have to develop an equation in the x-axis and one in the y-axis, and then either use substitution or another method I'll show you. So we have a few things we need to write down in the x-axis that we know and in the y-axis that we know. And if you're struggling with how to start these problems, a drawing is always a good idea. First thing. Second thing, you should always be writing given information. So in the x-axis, there's absolutely no acceleration. We know that it is 0 meters per second squared. And the proof is right where you sit as you're watching this video. If there was acceleration in the x-axis, your body would literally start to speed up either to the left or to the right as you sit in place, which makes no sense because this is not your everyday experience. However, we know that in the y-axis, gravity is acting, and there is always a downward acceleration in the y-axis of negative 9.8 meters per second squared. Now, the next thing is kind of a half given. We know that this velocity that's angled is made up of x and y, right? It's diagonal, so it's both acting in the x-axis, which we call VIX, and in the y-axis, VIY, right? So I zoom in a little bit so you can see what I'm looking at here. I would say my VIY is expressed in terms of this triangle. It is the opposite side in this triangle, which means we should use the sine function, but we should write the hypotenuse, which we don't know, times the sine of the angle. And similarly, for the VIX, it is the adjacent side to the angle. It is next to the angle, so I'm going to be using the cosine function. But before you write cosine, write the hypotenuse, then the cosine of the angle. So we know that our VIX is that, and our VIY is that. Okay. Now, what else do we know? Well, we know delta x. They're actually giving us delta x. It goes downfield 31.5 meters. And for delta y, if we consider the whole trip, notice it wants to know the highest point. It wants to know this point during the flight, but that's the second question. First, they ask us for the initial speed with which this ball is thrown. So for the whole trip, we know that we do not change y position. And for some of you, you might think that's a weird idea, but think about it. What is displacement? It is the change in position. So if you start on the ground and you end on the ground, then in the y-axis, you do not change position if you consider the whole flight, okay? So there's 0 for the whole flight. And time is that bridging quantity. It bridges the x and y. The time is the same for both axes. So I need to develop two equations, and I like to use the final velocity independent equation. What? I'm talking about this one using the equation that does not have final velocity in it. Notice you don't have final velocity here, you don't have final velocity here. So this is the one to go to. Now, AX is 0, so we call that 0. 0 times anything is 0. So we simplify this to be delta x equals VIXT. However, I'm going to put in VI cosine 40 times time. So I substituted in for VIX this expression. Let's go to the delta y, same idea. We're just going to change everything to y's instead of x's. And here we have a different 0. While acceleration was 0 in the x-axis, in the y-axis we know it's not, but we do know that for the whole trip, my change in y is 0, and therefore I can write 0 equals, what's VIY? Expressed as VI, it is VI sine 40 t plus 1/2 AY t squared. Okay, I'm going to divide everything by t. And 0 divided by t is 0. This t cancels that t. This t cancels one of those t's. And we're left with vi sine 40. Now, 1/2 of negative 9.8, right? 1/2 of negative 9.8 would be negative 4.9. And it would be meters per second squared. But right now, I'm just going to leave the units out so the expression doesn't get very cumbersome. I will now take this and add it to the other side. So I'd have 4.9t equals vi sine 40, like that. All right, I'm going to move this so we have a little more. So we're going to see that thing bouncing up and down. All right, I'm going to call this equation 1 and equation 2. On one of my other videos, what I did here was I substituted. Actually, I didn't substitute. I took this and I divided this equation by this equation, and I was able to cross out my VIs. But in this problem, they're asking for VI, so I'm going to handle it a little bit differently. What I'm going to do here is solve this expression for t. So let's do that. T equals VI sine 40 divided by 4.9. And now I have an expression for time, which I can then plug in for that time. So coming over here, I'm going to write delta x off of equation 1 is VI cosine 40 times this thing, VI sine 40, all divided by 4.9. And the cool thing is we've got nothing but VIs in this equation. Notice we know delta x. We know we can calculate sine and cosine of 40 very easily, and that's obviously a constant right there. So how do we isolate VI? Here's how I'm going to do it. I'm going to go ahead and rewrite this as delta x equals VI squared. We have VI times VI times the cosine of 40 sine of 40 all divided by 4.9. Let's take this whole thing and move it over. Let's see if you follow what I do here. I'm going to say VI squared equals, I'm going to flip the equation. I'm going to multiply both sides by the reciprocal of this. So then I would have delta x times the reciprocal of this stuff is 4.9 over the cosine of 40 times the sine of 40. Now I could have shown that, multiplied this side by this and this side by this, but that's a lot to write. So this kind of speeds it up for us. Notice I'm going to take the square root of both sides in order to isolate VI, and I will get the following expression, VI equals, and let's plug in numbers now. My delta x is 31.5 meters times 4.9 meters per second squared all over cosine of 40 times the sine of 40. And there you go. We're going to plug in all that stuff to the calculator right now and get an answer. And if you struggle with doing all of this in one shot on your calculator, then do it in pieces. There's nothing wrong with that. Just make sure that you're not doing too much at once if you don't know how, okay? And I get an answer, VI equals 17.7 meters per second. There's my answer. That's a good throw. Thinking about that, right? 17.7 meters every second. So when it's first thrown, that thing wants to travel 17.7 meters in 1 second. Now we know it begins to slow down on the way up in the y-axis and then speed up on the way down in the y-axis. But that x velocity, just a concept point that I'm making to you, that x velocity never shifts. And the other thing to realize, and I see this as a struggle for students, is they think, oh, okay, there's my, is that my x or is that my y velocity? It's neither. It's actually this one right here, right? So if I was actually looking for one of these velocities, VIY or VIX, I would have to do 17.7 times the sine of 40 or 17.7 times the cosine of 40, all right? Okay, so that's part A, it's done. Let's look at part B, and B will ask us to find the maximum height. So I always turn to this kinematic equation when I'm looking for my maximum height. That's the one. Now I need to make it specific to the y-axis. So my final y velocity squared equals my initial y velocity squared plus 2 times my y acceleration times my delta y. Now we are talking about our maximum height, so I'm going to call this max. And also, if you see that I put in these x velocities, think about what's happening to our y velocity. It's thrown initially with a pretty big x and a pretty big y, but in the next moment, that y velocity, as I said previously, starts to slow down on the way up until we get to the top. And at the very top, our the final y, if we call that the final position of our problem for part B, our v final y would be 0 meters per second. That makes this 0, and we would get 0 equals VIY squared plus 2AY delta Y max. Let's talk about rearranging this verbally, and then I'll just put that final result. I'm going to subtract this to the other side, and then I will divide both sides by 2AY. So doing that would look something like this, right? Okay. And now I'm going to go ahead and plug stuff in. So, oh, let's not forget that's VIY, right? So VIY would be 17.7 times the sine of 40. And I've said this in past videos. Remember, that square does not apply to that negative. That negative resulted from us subtracting this over. So we just square the VIY divided by 2 times negative 9.8 meters per second squared. You can see right now the negatives are going to divide out. So on your calculator, I wouldn't even bother with putting those negatives in. Let's get our delta y max right now. Putting in my calculator, I will do 17.7 times the sine of 40. And I want to show you what I'm doing just in case you need help with this. So actually what I did is I put the entire numerator in parentheses. So there's the closed parenthesis for the sine of 40, but then there's another closed parenthesis with a squared. I want to make sure that squared applies to everything in the numerator there. I'm going to press equals, divided by 19.6, and we get 6.604. Okay, now if you're like, well, you shouldn't be pressing equals in between, just do it all at once. Okay, let's do it all at once. 19.6 is 2 times 9.8. And you see we still get practically the same exact result, 6.6. And honestly, I'm going to leave it there, 6.6 meters. I already have my equal sign. Whoop, there we go. There is our answer. Done. Have a great day. I'll talk to you soon. If you have other questions, make sure to leave them in the comments.